Okay, here we are on page 6 looking at example 21 in the differential equations packet, where population y grows according to the differential equation dy dt is equal to ky. So immediately I know that we're dealing with some exponential function here, where k is a constant, t is measured in years. If the population doubles every 7 years, find the value of k. Find the value of k if the population triples every 9 years, and then can we get some sort of general equation for k? And so, if it's of the form dy dt is equal to ky, then I know y must be of the form y is equal to c e to the k times t. Again, that's just true from what we had up here. It's true just from our knowledge of the derivatives of exponential functions. So it says, if the population doubles every 7 years, find the value of k. So what that means is when time is 7, that the amount or the population at that point is going to be whatever we had initially doubled. So in other words, our population is going to be 2 times c. So I can go ahead and substitute y is equal to 7, or I'm sorry, y is equal to 2c, time is equal to 7, and let's see what we get there. So I have 2c is equal to c e to the k times 7. We can go ahead and divide both sides by c in this case. So I get just 2 on the left side, e to the 7k. To cancel the e, we're going to take the natural log of both sides, so I get the ln of 2 is equal to the ln of 7 e to the 7k. ln and e will cancel. So I get the ln of 2 is equal to 7k. We go ahead and divide by 7, and so k is equal to the ln of 2 over 7. Now we are looking for a general equation of a k, so I don't want to read too much into it right now, but we can take a look and see where do these numbers here, 2 and 7, show up. Well, the 7 we see here, and the 2 we see right here in the word doubles. So if that is the case, then we should see something similar down here, where maybe it's a 3 because it's tripling, maybe it's a 9 because it happens every 9 years. So let's go ahead and take a look. What is the value of k if the population triples every 9 years? So again, we're dealing with when time is 9, y is going to be 3 times c. So our equation now looks like 3 times c is equal to c e to the k times 9. Divide both sides by c. So I get 3 is equal to e to the 9k. Take the ln of both sides. And I'm left with ln of 3 on the left. The ln and e cancel. 9k on the right. Divide by 9. K is equal to the ln of 3 divided by 9. And so if we want a general equation for a, we see what's going on here then. I know that k is going to be the ln of, well, what happens to the population? Does it double? Does it triple? Does it quadruple? Is it multiplied by something? So what we're going to do is we're just going to call this the ln of the growth factor, factor implying multiplication, divided by the time that it takes to do that. So we're going to call it the time, t. Now we've actually seen this. Last year when we did radioactive decay, and I gave you that formula that Q is equal to Q naught e to the KT, we solved this and we found out that K was always going to be the ln of 1/2 over the half-life. Well, think about that. 1/2 is the growth factor. Every so many years, the amount of this radioactive isotope halves, it's cut in half. And the half-life is the time it takes for that to happen. And so what we did last year is pretty much exactly what we're finding here with K. In the next video, we'll go ahead and we'll talk about separating the variables, and we'll run through a few examples.